Hello everyone. So we have discussed about the experimental methods to obtain the EOS, equation of state of shock waves. So in this lecture we will discuss about the theoretical calculations of obtaining the EOS, the equation of state. So the theoretical calculations, we can determine the shock parameters from first principles. You know that the first principles are the first basis of or like propositions or assumptions. Those cannot be deduced from other principles. So and also it is possible to calculate this in few cases, the equation of state, and for this theoretical calculations, these theoretical calculations uses quantum mechanical calculations, that you know the quantum mechanics that involves the consideration of subatomic the structure. So let us imagine a group of atoms compressed together. Let's say I will draw only two atoms here. So this is a nucleus and we have electron shells around it. So this N is the nucleus, and then we have electrons here, we have electrons on the electron shells, and then we will draw one more atom with nucleus here and these electron shells here. So these are electrons. This is just a representative image. So if we compress it, let's say the group of atoms, we are drawing only two of them. So if we compress them, we know these electron shells will interpenetrate, and there will be very high force in between these atoms. So high forces, and these are high forces. When you compress it, high forces will generate, but they are short range force. It involves only that interatomic distances, short range. So we have you studied this in during our engineering or even earlier classes, that we can draw this energy versus separation distance diagram for these interatomic interactions, that we know energy versus x, which is your x is our interatomic distance, or we can write separation distance. So this curve, you most of you know that. So it looks like something like this, and then from that we can even have force versus interatomic distances. So this is the point of minimum energy. So this point, this separation distance, let's say we say x naught, the x naught is the equilibrium separation distance. So that means the atom will be at equilibrium if they are separated by that much distance. And then for force, we know that if we take it here, the force will be 0 at that it will look something like this, because if we have higher interatomic distances than this separation distance, then it will have attractive forces here, attractive forces, and if you go below the interatomic, that equilibrium separation distance, it will have a repulsive forces. So that means when you are compressing the material, it will have repulsive forces, and with decrease in separation distance, the interatomic forces will increase, and that will increase to a very high level. So I think we should have it like a different slope, not like this. So slope will so, and then again from this force separation distance, that plot, we can get pressure versus volume plot. So this is this will look like something like this. So this slope will be higher here and this slope will be lower here. So that means the increase slope increases with increasing pressure. So this is called, this diagram is called isothermal compressibility curve. Compressibility curve, that's actually isothermal, that is at 0 Kelvin. 0 Kelvin, and so as I mentioned, so this pressure volume curve can be obtained from this force separation distance curve. So these PV curve, so that means the pressure volume curve can also be used to obtain the shock Huguenot curve. So earlier researchers, they obtained shock compression curve for large number of materials by applying high pressure, but these isothermal curves, so those isothermal compression, whatever we saw just now, isothermal compression curves are not available at higher pressures. At higher pressures, you can see the much higher pressures, like in pressure greater than 10 gigapascal or so. So there is another method, that's why, which is more useful. Another method useful is called ME, GREU, Me-Grenet method. It is pronounced as I think Grenet. So these two dots for difference in pronunciation for this, I think this German word. So so this is called Me-Grenet UOS. So this is another theoretical calculation. So this is important to this UOS is important to determine the shock and shock response of the materials, or especially we can also do it even for the porous materials. So there's a constant involved in this equation of state, that is Gruney constant. So that can be that constant can be obtained from statistical mechanics. So statistical mechanics, as some of you will know, as opposed to continuum mechanics. So continuum mechanics is another one. So continuum mechanics considers the material as continuum, without any gap or hole, but in statistical mechanics it treats as the material as group of atoms, and actually the statistical mechanics, it deals with the energies of individual atoms, and it arrives at thermodynamic relations. That means that can be related to the energies of the individual atoms can be related to the thermodynamic relations, like thermodynamic relations that you know, so that can be connected. So now that as you can understand, the continuum mechanics is different, and statistical mechanics is different. So to get the constant used in May-Gruney UOS equation of state, that is the Gruney constant. So what we need to use some theories from statistical mechanics. In this treatment, these atoms are assumed as oscillators because of the atomic vibration. We discussed in one of the first classes about the atomic vibrations. So atoms are assumed as oscillators. So energy of an atom due to this oscillation is nh nu. So it is it's called nth level oscillator, and this is Planck's constant, and then this is the frequency of vibration or oscillation of those atoms. So also there is one state called ground state. That ground state energy is half h nu, so which is not included in that. This energy and this is different. So ground state means that the total energy of the electrons cannot be lowered at that state. Total energy cannot be lowered by transferring electrons, lowered by transferring electrons. So the total energy of an atom, or let's assume a group of atom, that means 1 gram, let's say, of atoms, 1 gram of atoms of a material. Now we can write E equal to the potential energy. I will write PE for potential energy, and then the vibrational energy. vibrational energy. So, of the atoms. So, now the potential energy we can write is phi, and then vibrational energy includes both the ground state and then the higher level state and nth level. So, what we can do is we have now 1 gram of atoms. So, there are not only single atom. So, we will write the summation from j equal to 1 to 3n. I hope you know about this summation signs. So, this h is the Planck's constant, will be constant, and the frequency of vibration it will take for different atoms. So, then j equal to 1 to thrice n h nu j n j. So, here why we are writing 3n, because we have n number of atoms and 3n because 3 oscillators per atom, which means in 3 oscillations in 3 directions. So, if you see, if you assume one atom here, then oscillations are like this direction, perpendicular direction, and the perpendicular to these 2 directions will be, we can write it like this, and then this will be, let us say, the frequency here, this oscillation frequency nu2, and this will be again 3. So, similarly you have will have other atoms, other adjacent atoms will have similarly. So, you will have these frequencies 3, sorry, we can write let us say 4, 5, 6, 4, 5, 6. So, similarly you can get thousands of atoms probably in this group of atoms, or thousands or even more than that. So, now that is why you understood that we use 3n as one atom can be considered as 3 oscillators. The total energy we can use this total energy to find the thermodynamic potential Helmholtz free energy, and then this Helmholtz free energy can be used to get the pressure. We are discussing about shock wave, so we want to know the pressure. So, this Helmholtz free energy is a thermodynamic potential. This Helmholtz free energy we can write, let us say we can write it like HFE, just the abbreviation we are using. So, this HFE is a thermodynamic, this is a thermodynamic potential that measures the useful work obtainable from a closed thermodynamic system. At constant temperature and volume. So, I will not derive these equations, we just need to we want to just summarize it. So we'll just write the expression. We are not going to derive it. Don't worry about the derivations, and if you are interested you can go through the Mark Mayer's the book of dynamic behavior materials, which we referred as the textbook, that is in the chapter number 5, the shock waves equation of states. So this is the total energy E. So from total energy E, what we got is the Helmholtz free energy A, and A will be equal to minus kT. So K is the Boltzmann constant, minus kT natural logarithm of summation of, it is exponential minus E kT, that E there is a total energy what we found, and this is the expression for this is the total energy we talked about, and this is Helmholtz free energy, and then we will have the expression for pressure from Helmholtz free energy, which is minus partial of A with respect to V, then this will be at constant temperature. So differential of HFE with respect to volume at constant temperature will give us the pressure, and this pressure, I'll just write the final expression without going into the derivation. It will be it's a long derivation because it needs some statistical mechanics input here. So this expression will look like something like this, because it involves the total energy 3n gamma j. I'll tell you what is gamma j, and then half of h nu j plus h nu j e to the power h nu j kt minus 1. This is e to the power this and that. So so these terms it came from the statistical mechanics consideration. We are not going into that, but we are more interested in this parameter gamma j. So gamma j is minus partial of ln nu j partial of ln v. So v is the volume and nu j is the, as you know, that frequency of vibration at constant temperature. Okay. So this is the gamma j, and this relation, if you see this relation, that's a, you can tell that this is a relation between pressure and volume, that you can see, and also it's a bridge between between statistical mechanics and thermodynamics. As you know, when you say thermodynamics, it is basically we are talking about the macroscopic level, and in statistical mechanics we are talking about microscopic level. So why I said that this is the bridge, because the what we got here is a relation between pressure and volume, that is like thermodynamics, and from where we got we used some relations of statistical mechanics. As I told, these terms came from statistical mechanics, although we did not show the entire derivations. So that's why this is a bridge between statistical mechanics and thermodynamics. And so Grune simplified this and assumed that all the oscillations have same gamma. So what it says is that gamma is equal to minus ln V t. We do not have a gamma j here or gamma subscript j or that new subscript j. So it says that all oscillations have the same gamma. So that's the assumption to make it to simplify it. So this gamma, as Grune assumed this, and this is called Grune constant. Grune constant. So Grune constant will be required because we will write now the Mi-Grune equation of state. Grune equation of state. So that's what we were showing, that is a theoretical calculation of shock wave. So we are not deriving these equations, we just will write the expression. This is pressure at 0 Kelvin, and then gamma V E, which is specific internal energy, minus E at 0 Kelvin. So this is at 0 Kelvin. So as you know, E is the specific internal energy. So this is Mi-Grune equation of state. So what it relates is a state, a thermodynamic state, thermodynamic state of PVE state. It relates to PE at 0 Kelvin temperature, and it can also relate, we can do this PV state to relate to any other reference state. For example, what we can do is we can take a point on the Hugenoid curve. So that means then we can write P minus pH equal to gamma V. V is the volume, E minus epsilon H subscript H. So the subscript H means Hugenoid curve. A point on a Hugenoid curve is that subscript H. So this means that we showed this equation, but this means the pressure and specific internal energy at a point of Hugenoid, that is outside Hugenoid curve, of Hugenoid, to this relate to a point P and E on the Hugenoid curve. So that means we wrote it as P subscript H and E subscript H. So this is this happening at constant volume. So at constant volume, so we can relate the pressure and internal specific specific internal energy at a off Hugenoid point to a point on the Hugenoid, and this Gruney constant values for many materials are available on literature. In literature, not for all the materials that we know that, but for many materials it is available. And if you want to approximate, a practical approximation is gamma equal to twice S minus 1. You can write this as approximation. So twice S, you know what is S. This comes from the linear the equation of state. We know that C naught plus S U P. So that S we are using here, this is twice S1. That's a approximation you can assume. And then another approximation is that gamma by V is equal to gamma naught V naught equal to constant. So these are at zero pressure actually, gamma naught V naught at zero pressure. So this can be also sometimes useful, and this gamma is actually assumed to be a function of volume. So so this is for what we talked about for Gruney equation of state. So we will now talk about equation of states for alloys and mixtures. So before going to that, we need to know what is the difference between alloys and mixtures. So I will leave that part to you. So please study that what is the difference of alloys and mixtures. So the basic difference is the alloys have so nicely mixed that it has a homogeneous composition. So mixtures have separable structures, but for details you just please study about alloys and mixtures, that is important. So alloys for UOS equation of state for alloys, alloy is not very easy, although it is easier for mixtures. So we know that for many alloys the equation of state is already available. Let us say we write that some alloys are UOS for some alloys available in the literature. For some unknown materials, if we want to know for some unknown alloys, so we need to find the equation of state that we need to theoretically calculate. UOS for alloys is not very easy, so the theoretical analysis is complex. So we will try some interpolation methods which are easier. For an alloy, let us say in a single phase alloy, so the specific internal energy that E cannot be directly obtained from from the constituent E of the constituents. Why? Because there are other terms involved here. So these are like mixing free energy, configurational free energy, so these are additional terms, energy terms is required. So that is why, so EOS for alloy is alloy cannot be directly obtained cannot be directly obtained here. What we can do, as we mentioned that we use some interpolation method. There are different methods to do that, but we will go with the simplest one, very simple method, interpolation method, one of the interpolation method. So what we can do is we can just take C naught, these shock parameters C naught, we can take summation of mi C naught I, and similarly S equal to summation of mi Si. What is this mi? Mi is the weight fraction of the constituent. So you can use it for mixtures and you can use it for alloys, although alloys is not it's just a approximation which is not very, may not be very accurate. So basically C naught and S, you can understand this is the for the linear relationship equation of state C naught S UP. So these we can do it like that, and also the density will be rho naught summation of mi rho naught I. So that means if you have a alloy with let's say 60% A and 40% B, if we know the C naught and S for this A and B, so then what we can do is like C naught for the alloy will be 0.6 multiplied by C naught A plus 0.4 multiplied C naught B. So this is similarly you can do it for S or even for density. So this is very simple, but there are other rigorous methods involved for this mixtures and alloys. We just want to talk about this UAS for porous materials. For porous materials, let's say for powders, porous material, powder can be considered as a porous material. So people use gas gun experiments for powders, but we can also use theoretical calculations. So here we can use the Migne EOS, which will be P minus pH equal to gamma V E minus EH. So this H is for, let's say, that is for the solid material. So pH and EH on Hugenoid of the solid material, the Hugenoid curve of the solid material, the same solid material of the which the powder is of, so solid material, and then PE for porous material or powder, let's say porous material, and 1 by V is the density of the solid material, density of material. So basically these are the relations of, so this is the porous material, let's say we want to compact it, to be compacted. So you want to compact the material using pressure and then using shock pressure. So so this is the relation we need to follow. And what we can do is we can use we can apply a Rankine-Hugenoid relationship, that those are nothing but the conservation equations, US of solid, let's say we assumed linear, that means US equal to C plus SUP, and then US of the powder, that is the porous material of the that is not known. So we want to know this US of powder. So you will apply the Rankine-Hugenoid relationships, and also we have the US of the solid. So how we can do, let's say for the solid we will write first solid. So mass conservation, which will be, you must remember this equation, we already found some equations, so we are not going to show you how we got that, but I hope that you already know we had in earlier discussion we mentioned this. So this is shock wave velocity. So H is for solid, the subscript H is for solid, and then momentum conservation, and then energy conservation. So momentum conservation is pH is equal to rho naught USH UPH. Then energy conservation is specific internal energy is equal to half of pH V naught minus V, and then US of the solid is USH C plus S UPH. So similarly for the powder, what we get is mass conservation is rho US UP minus equal to rho double naught. So double naught we use for the powder. So similarly for momentum, and then energy conservation, momentum is P equal to rho double naught US UP equal to half of P V double naught minus V, and then US is what? So US is unknown, equation of state is unknown. So using these relations we are not going to derive it using the relations described in the last slide. So we can find a relationship between P and V, pressure and V, which is a very big expression, twice V minus gamma, that Grune constant, the C square V naught minus V plus twice V gamma V naught V naught minus S V naught minus V square, and where this V you can V has can be related with the particle velocity like that, and here US is P V double naught V, and then UP is equal to P V double naught V. So if we have this relationship in a plot, that's a specific volume V by V naught and the x axis V by V naught, and the pressure on this axis. Let's say we have a powder which specific volume 1.95, 0.9, 0.85. So what will happen is, if we can draw the solid curve like this is solid. So if we take some other curves with the powder, so the powder curves will look like this. I will tell you what are these curves. Let me first draw it. So this is for, let's say, for 90% relative density of the powder, let's say 90%, 80% and 70%, 60% and 50%. That means this is 50% porous. So this is for solid and others are powder. So it will look something like this. So the plots are not very clear here, but you can check it from your the textbook. So this is basically what we talked about, equation of state for porous material. So we will discuss in the next class. We will discuss about little bit about the temperature rise due to shock wave, and also we will talk about the shock wave interaction, the reflection in the next lecture. Thank you.